Welcome to today's lecture. I am covering lecture series on the subject Fundamentals of Electronics Engineering. That is the first year subject. And today's lecture, in today's lecture, I am going to discuss few numericals on Opamp. So, as we all know that Opamp is a very important topic in our electronics. So, let's see. First of all, let's cover with the basic concepts before solving the numericals on Opamp, because these two are the very important rules, that is the virtual short circuit and virtual ground. So, as we all know that this is the basic circuit of an Opamp, and an Opamp is having an inverting terminal and the non-inverting terminal. So, this terminal with the negative sign is considered as inverting, and the terminal with the plus sign is considered as a non-inverting terminal. So, there are two rules, that the virtual short, in short, it means that the two terminals are always at the same potential, that is the virtual short. And virtual ground is that if non-inverting terminal is grounded, then the inverting terminal will automatically be considered grounded. Let's see why it's happening, why we are taking these two rules. Let's see. So, as we know that Opamps have high input impedance and low output impedance. Since it is having very high input impedance, so the impedance over here is very high. So, it will not allow any current to pass into it. Okay. So, this is the first concept. Therefore, for ideal Opamp operation, the current flowing through the input terminals of Opamp is assumed to be 0. For a non-inverting Opamp, the inverting pin voltage is equal to the non-inverting voltage without a direct short between the two terminals. The equal voltages on the two terminals occur through the virtual concept. So, this is known as the virtual short. So, what does that mean? If there is whatever the voltage is there on the non-inverting terminal, the voltage at the inverting terminal is considered the same. That is the virtual ground concept. And why is this happening? Because there is no current flowing through it. So, the two terminals are considered at the same potential. In an inverting input configuration, the inverting input is always mentioned at ground potential due to the non-inverting input ground potential. So, if the non-inverting terminal is at the input ground, so the inverting terminal will automatically be considered at the ground. So, this is known as the virtual ground concept. Although it may be having any voltage applied to its terminal, then also it will be considered the grounded. So, this is the virtual ground. So, this is what is it's saying, that even if the inverting input is powered by a 5-volt supply, the inverting in terminal voltage is equal to ground. That is why it is known as the virtual ground. Virtual because it is not actually grounded, but it is considered grounded. And why is this happening? This is happening just because of this concept, that the input impedance is very high and the voltage gain, input voltage gain of Opamp is very high, near equal to infinity. So, these are the two reasons. So, now in these numericals we will use these two concepts. What are the two concepts? Virtual ground and virtual short. Let us see how we are using these concepts. So, this is a simple numerical. Determine output voltage for the given network. What you have to find out? You have to find out this voltage. How will you do this? You have to consider this as V1 and this as V2. Okay. So, now at the terminal V1, always remember this rule, apply KCL at V1, and then in the next step apply KCL at V2. Let us see how. When you apply the KCL at V1, the expression will be V1 minus 2 volts upon 2K plus V1 minus 6 volts upon 2K will be equal to 0, because the current going into the terminal, that is input current, is equal to 0. Why it is considered 0? Due to the high input impedance. So, current flowing into the input terminal is considered always 0. So, we are left only two branches, that is branch 1 and branch 2. So, V1 minus 2 volts upon 2k plus V1 minus 6 upon 2k is equal to 0. So solving this, you will get 2V1 minus 8 equal to 0. So you will get V1 equal to 8 upon 2, 4 volts. Okay. So the voltage V1 will be equal to, this is V1. Now you will use this voltage when you will be making the KCL at this terminal. Now apply KCL at V2. V2 minus 0 upon 2k plus V2 minus V0 upon 6k equal to 0. You are having this branch, you are having this branch. The input current going into the terminal is 0 due to the high input impedance. So you are left only with two branches, V2 minus 0 because it is grounded upon 2k, this is expression, plus V2 minus V0 output voltage upon 6k. So now, since using the virtual short concept, the voltages at these two terminals V1 and V2 are always equal. So the voltage, that is V1, obtained by using the first KCL, says it is V1 is 4 volts. Now you will consider that V2 is equal to V1 using the virtual short and virtual ground concept. So substituting the value of V1 instead of V2 in this expression. So V1 is 4 volts. Here also 4 volts. So this is 12 volts plus 4. This will give you 16 volts. This is how I have solved this. This was a clue. So this is how any expression, any Opamp numerical, the solution to any of the Opamp numerical depends on these rules, that you have to apply KCL at node 1, that is the non-inverting terminal. First of all, you will always solve the voltages at non-inverting terminal, and in the next step you will solve voltages at inverting terminal. So first of all, consider the non-inverting terminal, apply KCL and come up with the voltage, find out the voltage at this terminal, and in the next step you will apply the KCL at inverting terminal, and using the concept of virtual short or virtual ground, whatever applies to your numerical, using the concept you will consider the voltage as V2 equal to V1 and substitute the same. So in this way you will be finding the output voltage. So here V0 will be equal to 16 volts. So I hope this is clear. Let's come up with the next example. Determine output voltage for the given network. Okay, again you have to find out this voltage. So what you will do? First of all, apply KCL at this terminal. Consider it as V1 and this is V2. So apply KCL at V1. V1 minus here 11 volts upon 20k plus another branch V1 minus 0 upon 20k. Again the input current in this branch is 0 due to the high input impedance. So we are left only with two branches. 2V1 equal to 11, V1 equal to 11 by 2. 11 by 2 volts. So this is the voltage at V1. Now let's apply the KCL at V2. Again V2 minus 7 volts upon 100k plus V2 minus 7 volts upon 100k plus another branch is V2 minus V0 upon 100k. Yes, and the third branch, to the third branch the current is 0 due to the high input impedance. So again solving this, 2V2 minus 7 is equal to V2 plus V2, that is 2V2 minus 7 is equal to V0. So again 2V2, substituting the value of V1 equal to V2, because by using the concept of virtual short. So again substituting the value of V2, 2 into 11 by 2. We are substituting the value of V1 instead of V2. Minus 7 is equal to V0. 2 cancel, 4 volts is equal to V0. So this is how we solve this numerical. I hope this is clear. The same rule applies to all the numericals. Let's discuss another numerical. Okay, so we can see that here the positive terminal is grounded. Positive is V1 and this is V2. So let's take V1 dash and V2 dash for the ease, because V2 and V1 are already there, and it is given that V1 equal to V2 is equal to 0.15 volts. So let's solve. So using V1 dash is equal to 0. Okay. Now at negative terminal, V2 dash minus 0.15 volts upon 33 plus V2 dash minus 0.15 volts upon 10K, 33K and 10K, plus there is another branch, and this branch the input current is 0 because of the high input impedance. So another branch connecting to the output is plus of V2 dash minus V0 upon 330K is equal to 0. Now let's solve this. Since V1 dash is 0 and using the concept of virtual ground, V2 dash, that is the voltage at the inverting terminal, will also be 0 due to the virtual ground concept. So putting V2 dash equal to 0 minus 0.15 volts upon 33K plus minus 0.15 volts upon 10K plus minus, so we can take this on the other side. So let's take this on another side. Solving this, you will get V0 equal to minus 6.45 volts. Yes, you have to solve this by taking LCM from these two, 33K and 10K. So in this way you will get the answer V0 equal to minus 6.45. So we can see the difference between this example and the earlier ones, that the basic concept that we are using the both previous numericals was that we were using the concept of virtual short, because that positive terminal was not directly grounded. So that there we were using the concept of virtual short. But here, since the positive positive terminal is directly grounded, so we can use the concept of virtual ground in this example, and solving this you will get the result. So again you can see that the rule is same, that you have to apply the KCL at the positive terminal and then the KCL at the negative terminal, and using either of the concepts of virtual ground or virtual short, you can predict, that is you can take the voltage of negative terminal equal to V1, that is the positive terminal voltage, and in this way you will land up with the solution, that is the output voltage. So we can go for another example yet. Let's see again Again here positive terminal is grounded. Yes, you can take V1 equal to 0. So, we will take V1 dash and here we will take V2 dash. This terminal is V2 dash. Then solving the terminal at V2 dash, that is a negative terminal. Again V2 dash minus 0.2 volts upon 1K plus V2 dash minus 0.5 volts upon 1K plus another terminal is this one, connected to the output, and the current going into the input terminal is 0 as due to the high input impedance. So, the third branch that we will take is V2 dash minus V out upon 10K is equal to 0. So, again that is V2 dash is 0, here also 0 and here also 0. So, how we will solve this? Taking the that is the minus of 0.2 volts, then again minus of 0.5 volts, and okay, so here you will multiply it with the 10, okay, plus okay, now again you will take this on the another side, that is the V out upon 10K. So, in this way you will get the solution. Here is the solution, detailed solution, that you will get V out equal to minus 7. So, in this way while solving out you will get the V out equal to minus 7. So, this is how this is working, that you will use the, again you in this example what have you used? You have used the concept of virtual ground because your positive terminal was already grounded. So, you are considering V2, that is V2 dash, that is the negative terminal, equal to 0, that is equal to grounded. So, in this way you can applying the KCL, the only concept is applying KCL at the positive terminal first and applying KCL at the negative terminal. Again this seems bit complex, but yes, this is the this is very simple yet. Let us see how you are going to solve it. This is inverting, this is the inverting configuration of Opamp. So, how will you solve it? In such examples where positive terminal is already grounded, how can you use it to find this, to find V naught dash? How will you find it? By applying the formula of RF upon R1 into V input, directly applying the formula. So, RF is this is RF, this is R1 and this is V in. So, RF is why negative? Because you are applying the voltage at the negative terminal. So, this is the inverting configuration. So, minus of 330K upon 33K and input is 12 millivolts. So, this is minus 10 into 12 millivolts, minus of 120 millivolts. Yes. So, this is minus of 120 millivolts. Now, another part of the numerical says, this part, that here at the negative terminal the input voltage is minus of 120 millivolts. Yes, because we have solved it. So, here we are obtaining the voltage minus of 120 millivolts. At this terminal, at the negative, another negative terminal, we are applying the voltage of minus that is the 18 millivolts. This is RF and these are the R1s. R1. So this again at the positive terminal you can see here is the grounded. This positive terminal is grounded. So let's solve this again. Again this is the inverting terminal configuration because you are applying the voltages at the inverting terminal. So what will be the formula? Minus RF upon R1 plus RF upon R2, that is V1 and this is V2 is equal to V0. This is how this numerical will be solved. So minus here what is RF? Minus of 470 K upon 47 K into 120 millivolts. This is the expression for this part. Minus of RF upon R1 into V1. Okay. Another is plus of again 470 K upon 47 K into 18 volts. This is minus of 120 millivolts. This is in this way the expression is there, and solving this expression what will you get? This will be cancelled, you will get 10 here, this will be cancelled, you will get 10 here again. So minus of minus 120 millivolts plus 18 millivolts, this is your answer. So the answer will be, this is 10 multiplied by 10, 1200, and this is 180 millivolts. So your answer will be 1020 millivolts. 1020 millivolts. After solving this, you will get the solution as 1020 millivolts. So this is how the these types of numericals are solved. That you will first solve the initial part, the first part, and then you will solve the second part. So the output of the first part will be acting as the input for next part. So in hierarchy you can see another examples where you have another part as well, or you can have a parallel part with this as well. So you should know that the output voltage from the first part will be used as the input voltage for the another part. So obviously you will go from left to right. Many a times students get confused that what is the main input to this system. So this is what the main input is. This, by using this input you will get the output of the first part. By using this input, this output as the input to this part, you will get the final output of the Opamp. So I hope this is all clear to you, and so let's have a quick recap that there are two rules, that is the virtual ground and the virtual short. Virtual ground says that when your non-inverting terminal is grounded, so your inverting terminal will automatically be considered grounded. Although you might be applying any voltage to the inverting terminal, then also your inverting terminal will be considered grounded. That is known as the virtual ground concept, and you can use this concept in solving the numericals. Another concept is virtual short, that the two terminals, that is the inverting and the non-inverting terminals, are considered at the same potential. And what is the logic behind these two? Because the input impedance of the Opamp is extremely high, and the input amplification of the Opamp is also, amplification factor is very high. So due to these two rules, KCL at the positive terminal, that is a non-inverting terminal first, and applying this KCL you will get the solution, the answer to this. So that's all for today.